Welcome back, everyone. So this is section 6.1, confidence intervals for the mean, sigma sound. Okay, so just to give you a rundown of this week. So today is obviously Wednesday. Wednesday we are going to do section 6.1. On Thursday we are going to do section 6.2. On Friday we are going to do the chapter 6 project, right? Chapter 6 project, but honestly, it's like an in-class thing, okay? You will get it done. You will get it done in class, okay? So you do not even need to worry about that.
A bit of a small QR code.
Again, Matt wants to do a statistics class NCAA tournament bracket, so feel free to join in with that QR code. So section 6.1 today, section 6.2 tomorrow, and that is honestly it for chapter 6. There's only 2 sections in chapter 6 that we're going to do. Chapter 6 is all about confidence intervals. So what does that mean? That means and then we have spring break, right? And then we have spring break. So when we come back on that Monday, we're just going to, I'll give you the review assignment. We'll go over it on the Tuesday. And then on the Wednesday when we get back, we will take our chapter 6 test, because it's only 2 sections. So that's really where we're headed for that, okay? But again, we'll review as much as we need to. It's honestly not too bad, not too rough. All right, so let's take a look here. As the name implies, confidence intervals. We're going to be making estimations on certain parameters. Okay, we're going to be estimating population parameters. In this chapter, we only do 2 sections, but there are more than 2 sections. The first 2 sections deal with estimating the mean, estimating the population mean, which is kind of a useful tool because, is the population mean something that's easily available for a lot of topics? No, like the population mean is really difficult to figure out sometimes. Sometimes it's not. It depends on your population. If my population is all students in Mr. Laverick's statistics class in the 2nd semester, well, then my population is just you guys, right? But if I say my population is, all seniors in the state of Ohio, well, that's a lot of kids, right? That's a lot of people. So how do I really get a population mean? That would be really difficult. So what we can do is estimate the population mean. Section 6.1 and 6.2 would deal with population mean, and that's all we're going to do. Section 6.3, 6.4, and so on deal with population standard deviation. So you could actually do this again with standard deviation, but we're only going to focus on the mean. In this section, we will learn how to use sample statistics to make an estimate for the population parameter mu when the population standard deviation is known. So this section deals with, okay, if I don't know the population mean, but I do know the population standard deviation, which is kind of really weird. Like, how would we know them? How would we want to make an estimate for the mean and we know the population standard deviation? That seems kind of weird. But section 6.2 tomorrow is basically the opposite of that. So if we don't know the population standard deviation, then what do we do? Which is a little bit more logical of a case. Like if we don't know, if you're trying to estimate the population mean, you probably don't know the population standard deviation either. But let's say for today, let's say that we do know the population standard deviation. Let's say that our sigma is actually known. Okay, let's say that we know our sigma. Okay, so our definition of a point estimate. A point estimate is a single value for a population parameter. Now, a point estimate can be considered for both the mean and the standard deviation. We're not really going to cover point estimates for standard deviation. We're just really going to cover point estimates for means. Okay, the most unbiased point estimate for the population mean is the sample mean, right? Our where we start is the sample mean. That's where we're going to come from. We're going to take a sample of that population. We're going to run the sample mean, and we're going to base our prediction, our estimation for the population mean off of our sample mean. Okay. Assume that gas mileage among the faculty's cars is normally distributed. Find a point estimate for the population mean given the following data. So really all I'm going to be doing here is just finding the sample mean, right? Our population mean can be estimated using the sample mean. And I don't know why do I use this number again? How often do I use this number? Because I really don't want to plug all those in. Yeah. So what if I had said, I don't want all these numbers. What if I was going to do this? And maybe this. Okay, there we go. That's a bit better of a data. The same things can be reached just having a smaller data set. I don't know why I was punishing myself. 34 plus 21 plus 19 plus 35 plus 17 plus 15 plus 32 plus 22 plus 19 plus 20 plus 37 plus 23 plus 29 plus 32. Okay. And divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Divide by 14. All right. 25.36, which is actually pretty close to the big one I had. I just in my notes. 25.36. 25.36. Okay. So here is our X bar, right? There is our X bar. What we're going to be doing today is saying, well, if I create a sample mean, okay, I'm going to take a sample out of there, and I'm going to say my population mean is probably somewhere close to this. As long as my sample is random and representative, I would say that's probably going to be pretty close to my population mean. The probability that the mean is exactly what we got is nearly zero, right? It's a very, 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 very small chance that the population mean is exactly equivalent to a sample mean. I'm talking about exactly equivalent to a sample mean. Instead of making a point estimate, we could make an interval estimate. See, the difference between a point estimate and an interval estimate is saying, well, if I know the sample mean, I'm going to say my population mean has a range of values in between certain values. So what I mean there is I'm changing it from just one single number, where the probability of that actually happening is quite small, to having an interval, which raises the probability that my true population mean is somewhere in there, right? And the wider I make that interval, the higher the probability that mean falls in that range. Right? So an interval estimate is an interval or range of values used to estimate the population parameter. So in this case, our population mean. I'm going to take my sample mean, and I'm going to give a range of values, and I'm going to say, okay, I bet my population mean is going to fall between certain values. So for example, my mean was 25.36, right? 25.36. Let me bring this over here. Oops. Come on, buddy. Come on for the ride. Here was my interval estimate. We may want to have a margin of error of 3. So what if my margin of error was 3 for my mean of 25.36, right? So I'm saying if I know X bar was 25.36, my sample mean was 25.36, and I was okay with having a margin of error of 3 units away. Well, that would mean that my population mean is somewhere between, okay, 3 units above, 28.36. 3 units below, so 25.36 minus 3 would be 22. Oh, duh, 22.36. Oh, no, not or equal to 25.36. Okay. Somewhere in between there.
22.
Oh, yikes. 22.36. Thank you. Yes, I did. 22 points. Now, how confident am I that my population mean falls somewhere in there? I mean, I feel pretty confident in that statement, right? Now, unfortunately, pretty confident isn't very mathematical, right? We like to deal with numbers, like, so how confident actually are you? That's what we're going to be studying in this section. That's what we're calling confidence intervals. Okay. Before you find your interval estimate, you first want to determine how confident you want to be in that interval. Okay. That your interval truly contains the population mean. And that's where we have to start talking about our level of confidence, the mathematical value of confidence. The level of confidence is the probability that the interval estimate contains the population parameter, that our interval contains the population mean. We have to first decide, okay, how close or far away are we okay with, basically? How much give and take are we allowing ourselves? You know, because if I allow a bigger margin, you know, I'm gonna increase my confidence, right? If I say, you know, if I go 10 units above or below, how confident am I that that gas mileage is somewhere in there? I'm extremely confident, right? So my confidence goes way up if I increase my margin. As I decrease my margin, my confidence should go down, right? As I decrease my margin, my confidence should go down. For example, we're going to use the lowercase letter c. Sorry, still writing that. I'll go bring this over here. Come on. Come on. Come on. There we go. So we're using the lowercase letter c for confidence. So for example, if confidence was 95%, so really high confidence level, right? If confidence level was 95%, then 2.5% of the area is to the right and 2.5% of the area is to the left. Think of it like the bell curve, right? Think of it like the bell curve. Because I'm saying, okay, here is my normal distribution. Here is my mu, right? I am saying I am 95% confident that my interval contains my mu, right? I am 95% confident. You got to think about it this way. I've got 5% left over, but I could be overestimating or underestimating, right? It actually could come out above or it could come out below. So you have to think that there is 2.5% over here and 2.5% over here. Okay. So what we could do is find the critical values where this comes up. Now the critical values would be the negative, and that should be a little subscript. That should be written as negative ZC and ZC, right? Negative ZC and positive ZC, such that this happens. Oh, that sounds like a quiz test question that we just had, right? I want to find when 70% of the data fits between negative Z and positive Z. Oh, now I'm looking at when does 95% of the data fit between negative Z and positive Z. Sorry. Now, the nice thing is, if I look at my standard normal distribution table, what I can do here is say, oh, look at this. We didn't really used this yet, but you know that little box down there? That says level of confidence. So if my level of confidence is 95%, if my level of confidence is 95%, well then I can say that I can use ZC as 1.96. See, it's kind of already done the work for you. Remember that 70% problem that we had? We needed to take our 50% and say, okay, there's 2.5% above here, so I want to find the value at 97.5%. And then I have to go look in here and say 97.5%. But it's already done that work for you because it knows that you're going to want to go above and below the exact same amount. Let me get your quiz for you. Hold on. Hold, please. I'll give you guys something to talk about. Rhode Island, neither a road nor an island. This guy's.
Well, it's not Silver Road. It's like Florida.
Yeah.
Some goofy,
No. Statistics. So, I'm going to put the white copy here. Come on out.
What was the back discussion question? Oh, the conspiracy theory where there were bombs in the World Trade Center and that's how the
I
towers
want to
fell.
see your computer
And not the planes.
on this table, and
How
you
about
can
that?
take the white copy.
That's pretty simple.
That happened in
Over
this.
to the computer there, pick up the white copy.
we can work hard.
Personally,
Yeah.
often BT or Ellie. So I can't really.
And we're back.
That's true. I wasn't there, but that's such a great way to refer to things that happened before your lifetime.
Yeah.
In my mom's living. I remember.
So again, the nice thing about this table is that the confidence intervals are already calculated for you. Now, the only bad part is that it's calculated for you for 80%, 90%, 95%, and 99%. So just those 4 levels of confidence. If you wanted to find a level of confidence outside those, then you would have to manually find it like that. Like for example, if you wanted to say you were, 60% confident. 60% confident. So 60% confident, you would have to say, well, okay, 60% falls here and here. How much left over? 40% for both sides, so 20% here, right? So what value would I be trying to find for this z-score? 80%. Then you would have to go in and find 0.8 and say, okay, 0.8 looks like it's 0.84. So your z-score would be 0.84. But the nice thing is this is already done for you. So you look at your table and you say, okay, confidence interval is 95%. 95, right? Yeah, 95%. I could say 1.96. ZC is 1.96. And that's a plus or minus, right? That's a plus or minus. Okay. Given a level of confidence, we can now find our margin of error. We can now find our margin of error. Basically saying, okay, truly, how far above and below our sample mean do we predict the population mean to be? How do we find that? Well, our E, our margin of error, capital E is denoted for margin of error, is ZC times sigma. Now, sigma is sigma x bar. And how do we calculate sigma x bar? It's sigma divided by square root of n. Because that is, and this is why we had to learn that sampling distributions of sample means. That's the sigma of sample excuse me. That's the sigma of sample means. Not sigma of my population. No. That's sigma of sample means. And how do you find sigma of sample means? Sigma divided by square root of n. Okay. And that is the value that you're going to be able to go above and below to create your interval. Okay. A couple things here. The sample's got to be random. and either the population is normal or n is at least 30. Okay, that's the same thing from our central limit theorem, right? Either the population has to be normal or n has to be greater than or equal to 30. So a couple stipulations there. All right, can we try a problem? Hold please, sir. What do you call a dog magician?
It's gotta be some kind of breed.
Dog magician.
A
Labracadabrador.
Oh, very good.
A labracadabrador. All right, here we go. Sorry, were you still looking at that, Kate?
It's okay.
You good? Okay. Suppose that you sample 100 adult Ohioans, and the sample average income is $35,000. We know that the population standard deviation is 6,000. See, this is we know sigma, right? Tomorrow we will not know sigma, but today we do. We know the population standard deviation is $6,000. Find the margin error for a 90% confidence interval, 90% confidence level, and then again for a 99% confidence level. Okay. So, looking here, what is n? 100, right? That n is 100. What is 35,000? Is that mu? That's x bar, right? X bar is 35,000. What is sigma? 6,000. Now we're going to use all those, but now what we're going to do is find the 90% confidence interval, and then run those exact same values for the 95% confidence interval. Well, yikes. I'm not having a good day today. Screwing up numbers. I messed up on an exponent in calc today, so threw off my problems. All right, anyway. Okay, so 90% confidence interval. So looking at my table, I go down here and I say, okay, what is my z-score for the 90% confidence interval? It's 1.645. 1.645. So ZC is 1.645. Okay. So to find the margin of error, E, remember my formula, which again is on the formula sheet, is ZC times sigma divided by square root of n. ZC, 1.645, times sigma, 6,000, divided by the square root of 100. So 10. So our error, now did we use 35,000 in that? No. That'll come up here in a second, but not yet. 1.645 times 6,000 divided by the square root of 100 is 10. 987. 987. Now, what does that mean? That means that I am okay if I want to be 90% confident that 987 could go above or below the mean, which means that above or below my x bar. So which means that I could have a range of values between 35,987 and subtract 987 from that x bar. And then I would say, okay, I'm 90% confident that my population mean fits in that interval. We'll do that in a second. Let's do a 99% error margin though. Now, what do you expect to happen with my error margin? As I increase my confidence, what do you expect to happen? Good. Well, I'm going to be more confident that my population falls between those intervals.
So there's the number good. Margin of error go down.
Enter tails.
Is it going to go up? Well, let's see. Is it going to go up or is it going to go down? All right, so what is ZC in this case? What is ZC in this case? Well, 99%. I go to my table. Oh, it's not on there. Oh, yeah, it is. 2.575. 2.575. That's just straight off the little table down here. If it's not in that little table, you got to go through that whole process of, like we did on the past test. So our error margin is going to be 2.575. 6,000 divided by square root of 100.
If you're more confident, wouldn't the error margin go down?
Let's see.
Well, it's not going to.
It's not going to, is it? You already know, based on the math, right? Times 6,000 divided by 10. 1545. So why is it going up? Because if I'm more confident, right? If I want to be more confident, I'm going to need to widen my range of values. You see what I mean?
Yeah.
If I decrease my range of values that I'm going to fall into, I have to be less confident. Does that make sense? So they kind of work inversely. Yeah. All right. So what is the true confidence interval, basically? Well, you take your error margin and you subtract and you add. That's how you create your confidence interval. You take your error margin and you add it, and you take your error margin and you subtract it from your X bar, and that's your range of values. That's your interval that mu could fall into. And that relates directly to probability, right? The probability that the confidence interval contains mu is that C value. So like you are 99% confident, that means that the probability that mu is going to fall into that interval is 99%. You are 70% confident, that means that the probability of mu falling in that interval is 70%. So let me just bring this over here. Should condense these slides a little bit. So let's construct, based off of the last problem, let's construct a 90% confidence interval and then a 99% confidence interval for the mean. So let's first start by our 90% confidence interval. So our 90% was 987, right? 90% was 987. And we know our X bar, straight off the last problem, was that 35,000 that we didn't use for our error margin, right? So our mu should be between 35,000, 987, and then I've got to subtract it away, right? 35,000 minus 987 gets us 34,013. 34,013. Okay. So I can say that I am 90% confident that my true population mean falls in this interval. Okay. 99% confident would do that exact same thing, but now I'm using that 1545. So mu is going to have a wider range of values. 35,000 plus 1545, and then 35,000 minus 1545. So 36,545 and 33,455. Does that make sense?
Yeah.
Okay. Nah, we don't need to do another problem with that. Okay. Last thing we'll talk about today is finding a minimum sample size to estimate mu. If we have extra time, I'll go back and do that problem, but I don't think we will. Okay, so this is saying, like, if I really want to estimate my population, what is the sample size that I would need? Like, this is a really important statistic. This is a really important piece of information here. If I know how confident I want to be in my interval, if I know I want to be 95% confident, and I know sigma, and I can calculate my error margin, I can then calculate, kind of like work backward and calculate n. And what is n? N is my sample size. So I can really say, okay, if I know this confidence level, if I know this error margin, if I know this sigma, I can now say, okay, this is the population I would need to find out my x bar to truly be that confident. Okay. Now, how is this calculated again? Well, my error margin formula, just reading it straight off here, is ZC sigma over square root of n, right? We just used that. So this is just solving for n, right? I divide by ZC, actually ZC sigma, right? I could put this up in the top. Divided by ZC sigma is equal to 1 over the square root of n, right? Multiply by the square root of n, actually kind of cross multiply. E error margin square root of n is equal to ZC sigma. And then divide by E, ZC sigma over E, and then square this whole thing, and that's where we get that. Okay? So that's just a manipulation of the error margin formula. Okay? So let's apply it. You want to estimate the gas mileage of teachers' cars? How many cars must be sampled if you want to be 95% confident that you're within 2.5 miles per gallon? If you know the population standard deviation is 8.1. Okay? And this is all reasonable. The only thing maybe unreasonable is the fact that you know the population standard deviation. That seems weird. Like, how do you know the population standard deviation if you don't know the population mean? But again, that'll come tomorrow when we don't know the population standard deviation. So you want to estimate the gas mileage of teachers' cars. How many cars? So you're looking for n here. That's what we don't know. Well, the formula is n is equal to ZC sigma over E. ZC sigma over E squared. That's going to be n. So what is ZC? What is ZC? Well, I go to my table. Is that 1.645? That number rings a bell. Oh, 95%. 1.96. 1.96. I've got 1.96. Sigma is 8.1. What's my error margin that I'm okay with? 2.5. Okay, so that's going to be 1.96 ZC sigma times 8.1 divided by our error margin of 2.5, and I've got to square this whole thing. So 1.96 times 8.1 divided by 2.5 squared. Okay, 40.33. So n is 40.33. So can I choose 40 people? No, I got to go 41 people, right? Because if I choose 40 people, that's not enough. I need to choose 41 people to meet my threshold. Right. Right. Does that make sense? All right. We can stop there for today. Let me turn off the video.